Okay, this is Cecilia A21, January 2011, question 2B on thermal physics. Okay, so this here, it's a difficult question because it's out of 4, okay, and it obviously involves temperature. And let's see what else it involves to see what we're working with here. So, a flask contains air at temperature of 17 degrees and is sealed with a rubber bung. A capillary tube of diameter 3 millimeters containing a short column of mercury is inserted into the bung. So what it's saying is we have this capillary tube, we have the flask, and we just have this here, air, and it's trapped by the mercury. Okay, the volume of trapped air is 40 centimeters cubed, and the arrangement is as shown. Okay, so at the minute we have a temperature, a diameter, and a volume. So I'm thinking here it must be volume and temperature. The flask is warmed, we heat it up. Calculate the temperature reached when the mercury column moves up 120 millimeters up the capillary tube if the pressure remains the same. Okay, so when looking at this, my first volume before I heat it up is 40 centimeters cubed. So I'm going to put that as my V1, okay? And the temperature at which my volume is 40 centimeters cubed is 17 degrees. Now, because this is thermal physics, we have to turn that 17 degrees into Kelvin by adding on 273 so that we get 290 Kelvin, and that's going to be my T1 value. So when we increase the temperature, the volume should also increase. So it's telling us, it's not telling us the new volume, okay, it wants to find temperature, but in order to find the new temperature we have to work with another volume. But what it is telling us is it is telling us the diameter of this tube, and it is telling us a length that this mercury moves up by. Now I've got this equation written here to show that we actually can calculate the second volume. So volume is equal to, you know, it's essentially 3 lengths multiplied by each other. The area times by length. Now this question throws in not only this to try and trick us out, but also a few other things. So if we look here, my volume is measured for V1 is in centimeters cubed. So if I want to look at V2, I have to work in the same units. So if V1 is in centimeters cubed, I'm going to have V2 in centimeters cubed. So that's going to be centimeters cubed. In order for this to be centimeters cubed, this has to be centimeters squared. And my length also has to be in centimeters, because obviously centimeters squared multiplied by centimeters is going to give me centimeters cubed. So what I need to do is I need to check, do I have my area and do I have my length, and are both of them in centimeters squared and centimeters. So looking at the information I've got again, I do have a length. I have a length of 120 millimeters. Now, as I've just said, that needs to be in centimeters. To turn it from millimeters into centimeters, I divide by 10. So my length is actually 12 centimeters. So put this here, it's 12 times some area value. We don't seem to have the area. However, this diameter is constant, so we can look at finding the area using the diameter here. Okay, so here I have the equation, area is equal to pi d squared, the diameter of the capillary tube, divided by 4. Now again, that's in millimeters. We need it to be in centimeters. So you just divide it by 10. 3 divided by 10 is 0.3. So all I've done here is I've just taken my area equation and substituted in D in centimeters. And when I do that, I get 0.07 centimeters squared. So I can then go and put this area back here into my equation, and when I multiply those two values together, I get 0.85 centimeters cubed. Okay, so you're probably sitting saying, well, my volume V1 is 40, why is my volume now 0.85? What we've just calculated is we've calculated the change in volume, how much the volume is increased. So my actual new volume, my V2 volume, is equal to V1 plus the rise in volume, which is this, what I've calculated here. So it's going to be 40 from here, plus how much the volume changed, 0.85, okay? And my new volume, V2, is going to equal to 40.85 centimeters cubed. Okay, so I now already have achieved some marks for calculating V2. But that's not what it wants us to find out. It wants us to find the temperature. So the equation that links both volume and temperature is this one here. V1 divided by T1 is equal to a constant, and that same constant is equal to V2 divided by T2. Now, they've given us V1 at the top, if you remember, 40, so I'm going to put that in. T1, it also gave us that, 290 Kelvin. And that's going to equal to V2, which we now just calculated, 40.85 divided by T2. Now, sometimes people can really confuse themselves when they're rearranging the equations. So what I like to do is I like to find this constant first and then use it for the second part. So when I do 40 divided by 290, I get my constant value to be, C is equal to 0.138, say, okay? And that's now equal to 40.85 divided by T2. So if that was a triangle, if it was C is equal to V2 over T2, my T2 is equal to V2 divided by C. So T2 is equal to V2 divided by C. So my V2 was 40.85. Left-hand problems there. I by my C 0.138. When I type that into the calculator, 40.85 divided by 38, I get a new temperature of 296.01, we'll say, Kelvin. Okay, so that is my T2, that's what I found. If they ask you for your temperature in Kelvin, that's what your answer would be. However, they usually don't. They want it in degrees. So to change from Kelvin back into degrees, we simply have to take away 273. So I'm going to do 296.01, take away 273. And when I do that, I get a value of 23.01 as my answer.